for who's here. So everyone is a physics teacher. Can you raise your hand if you teach? Is that right? Do people teach other disciplines as well, or just physics? Michael, what do you teach? Oh, 3.
I teach mathematics as well, and I'm getting training in data science as we speak.
Great. Okay, and Francette?
Yeah, I've physics, environmental science, and astronomy.
Okay. One of my favorite activities is environmental science, and so that gives me the great excuse. I think even in regular physics it should be talked about, but that gives me a great excuse to do it. Any AP teachers? Show of hands. Okay, IB. Okay, James does it all. Okay. Yeah, so my name is Matt Vonk. I teach physics at the University of Wisconsin River Falls, and I actually am just stepping down from being on the development committee for the APC test. I was in that role for, I think, 7 years, really enjoyed it, and love to be part of that process. I've been a long time reader also of the AP exams. And I'm one of the co-founders of Pivot Interactives. And my collaborator, Peter Bahacek, is a high school teacher in Mendota Heights, Minnesota. And we were trying to solve problems for our own classes. We thought we want our students to be more active. And if we can, in a digital format, provide them kind of authentic science opportunities for investigation, that would just make so many things. We could streamline a lot of the process and yet retain the really important essence of science. And so I'm going to share my screen now. Okay, and hopefully you can see that. And we're starting at the Pivot Interactives library. And so this is where our activities are located. I've narrowed it to physics, and you can see that we're looking at 24 of 278 hits. And there's some duplicates. Sometimes we do a couple of different versions of a very similar activity, so that's probably somewhat of an overcount. But our activities in physics are really well represented. And my favorite part of this is just looking at the activities. And so I want to jump in and do that. But I'd encourage you to kind of explore on your own. So the website is pivotinteractives.com. You can request a free trial for 30 days, or you can just browse the library as well. So the first one I want to look at is this. This is kind of our take on projectile motion. And so it took us weeks to build a laminar flow fountain. And so we did that. And so this is a high-speed video of it, and I'm stepping frame by frame now. And it took us a long time to kind of figure out the best way to cut a little notch in it so students would have something to kind of measure. And it turned out to be just beautiful, which is one of the reasons that I like this. It gives them really kind of intimate access to this, what would normally be kind of a mundane event. And then we provide students with the tools they need to analyze this. So they can measure the angle. There's an interactive stopwatch. There are rulers. And so using those tools, they can determine the initial conditions of the stream of water and then use that to make a prediction about how far it will go. And so then they make a prediction. Generally, we allow students to move kind of back and forth throughout the activity, but often when we have them make a prediction, we will lock the section. So they're kind of locked in. They have to make a prediction, and then they can't go back and change it. And so this is one of those cases where they make the prediction. They have to say, okay, I'm gonna ready to lock that section, and they can move on. And this is the same event recorded on a different camera that's farther away. So here you can see our high-speed camera very close to the laminar flow fountain. And you can see Joe's head. Can you see my cursor as I move it around? Okay, great. Joe's head up here in the upper left, kind of bending over, and he's just swings a blade through the stream and creates that. And students can determine whether their prediction was correct or not. What's kind of interesting is that the gap, the size of the gap grows. It's a little easier to see in the other video, but let me see if I can get it shown on here. And so right when he makes the gap, it's very small. And then over time, it increases. And so depending on which side of the stream students choose, they're going to get a higher initial velocity or a lower initial velocity. That will result in a different prediction for the range. And it turns out it's fine because the leading edge of this, the left side of the stream, actually does go less far than the trailing edge of the right side of the stream. But I was amazed how difficult even doing basic measurements of velocity are for my students. To me, this seems exactly the same as if I had said, here's an initial velocity, here's an angle, determine the range. But it's not. Like, students having to zero the protractor is hard for them. Zeroing the ruler, putting the ruler on 0 at the same time that you put the stopwatch on 0. Like, these are all real lab skills that are important for measuring and understanding how measurements work, that they would not get on just a pen and paper problem. I'm going to just pause there and see if there are any comments, reactions, questions. Also, how many of you are familiar with pivot interactives? So, okay, great. This is another favorite of mine. My business collaborator, Peter, is close personal friends with Jessie Diggins, the Olympic gold medalist in Nordic skiing. And so he talked her into coming and running up this hill. So this is our version of the incline plane. And so again, students can measure the angle of the incline, and they can measure her speed. And they can graph it, and they can see if her speed is constant or she's slowing down, and learn about kind of concepts of kinematics. Again, this is way harder than a word problem. Students have to think about where on her body it makes sense to measure. Do you want to measure her hands, her feet that are kind of going in fits and starts, or something like her forehead that seems to have a much more constant velocity? One of the things that I love about Pivot Interactives is that we give students a lot of control. So in this video, students can control the speed. And so this is real-time speed. She's running pretty fast. And then they can add a backpack. And she was such a good sport. We really loaded this. Was a heavy backpack. And you can noticeably see that she's working hard and going slower. And then another one of my favorites of this is on the third take, there happened to be a dog that was just in the frame and wanted to run up the hill too. He's like, I might not be an Olympic medalist, but I'm a golden retriever. So. And this is one that we did several years ago, but I think it really demonstrates the idea. And so let me just start by playing this. And so we have a computer, and it's connected to a subwoofer speaker that we attached a lever to. And so it will wiggle this big long spring that we stretched out on the near the floor of the lab 5 times. So 1, 2, 3, 4, 5. And then students from that one video can measure the wavelength, the frequency, the speed, the amplitude, and like those are kind of abstract concepts, but if students can actually be the ones kind of in charge measuring them, I think it makes it more concrete for them. But then students can change things. And so they can select 5 different frequencies, 5 different amplitudes, and 3 different tensions. So this looks like a single video, but it's actually 75 videos. 5 times 5 times 3 is 75 videos. And so students can kind of have a lot of agency to explore on their own. They can say, oh, like I wonder if I shake it faster, if the wave speed will increase. And we know that it doesn't, and we could tell them, or they could kind of discover it on their own. Or they could say, oh, I wonder if I decrease the amplitude, if it will slow down. Or they could say, what's the relationship between wavelength and frequency? And so different groups in the same class can kind of take their own course and do whatever they think is interesting. So let's jack up the tension, increase the amplitude, and do a high frequency and just see how that looks. Okay, and immediately you can see that the wavelength is shorter. This is still one of my favorites. This was another one that we did early on, and it's to measure the speed of sound. And so we lined students up on the football field on a beautiful kind of late summer day, and we had them shut their eyes and clap in time with the metronome. So this black box up here in the upper left, lower left, is a metronome. And they're just clapping as they hear the sound of the metronome. And so let's just watch it. And so there's 10 meters between each person. And then we're going to slow it down, and you're going to be able to see kind of the wave of clapping go from the front to the back. So here, Emma in the front, Isaac moves down, moves down, moves down. And using that, you can get a pretty reasonable speed of sound. And it's kind of intuitive and understandable for the students. When I first did this, and like I love it when I'm the one that learns things. When I first did this, I just took Emma and Max's time, the first and the last time of the claps, and I divided by 80 meters by that time to get the velocity. But then I was thinking, probably it would be better if I included everyone's data points. And so I made a graph. And I think it's this woman in the striped for the trial that I did clapped actually before the woman in front of her. And I was like, oh shoot, it's not going to work. This is going to screw it up. And before like casting, I'm not casting aspersions on any of them because it's really hard. Like, are you clapping kind of at the beginning? Or are you anticipating a little bit? Are you you want to really be sure that you hear it and then clap? And so there's no right answer, right? Kind of everyone is doing it as they interpret it. And so I don't know that one was right and one was wrong. But when I graphed it, even with that switch, the result was like spot on for 70 degrees, the velocity of sound in 70-degree air. Like it was, and it just convinced me again that like, if you can use many data points and graph it and do some kind of analysis, that's better than just taking the first and the last. Actually, before I move on, there are a few kind of just logistical things that I want to talk about. And that is that all of these activities are editable. And so I'm going to go back to the Pivot Interactives library. And these are the ones in the main library. And if you would like to assign it, kind of the workflow is that you copy it to your own library. And then once it's in your library, you can do whatever you want. And I know a lot of teachers, and everyone has their own style, their own kind of flavor, like the language that they use. And so we try to make them, all these activities, so that they're usable as is. But if you say, you know, this whole section goes off on a tangent that I don't really care about, I'm going to cut it, you can totally do that. Or if you want to say, I want to use language for potential energy, that's a little bit different than the language that's here. Like, you can totally make it your own, which is a really great feature. Another thing is that at my university, we use Canvas. Many of you probably use other LMSs or rostering services, and the Pivot Interacts integrates really well with those LMSs. And so you can assign it through Canvas or D2L or whatever you use, and the grades pass back and forth. And so it's just kind of a seamless interface in that regard. Talking about features, we've really tried to provide students a lot of in-app support. We created this pre-COVID and had the idea that, you know, teachers would just use it like I usually use it, by assigning it during class and kind of circulating as people are working on it. If that's your model, then there's a lot more leeway in how you write activities. They can be much more open-ended, and if students get stuck, you're there to jump in and say, oh, you might want to think about dividing by 2, or zero the ruler, or whatever. But during COVID, students, a lot of them were working on their own, and a lot more kind of on grade level students started using Pivot Interactives. And so we've tried to really increase the amount of feedback and support and auto grading that we provide. So you can see all of these are indicated how much, what fraction, what percentage of the questions are auto graded. And that's also a search parameter. So you can say, if I want to just see the activities in physics that are at least 90% auto graded, that leaves you 59 activities to choose from. And then if there are questions that you want to, or they're not auto graded, and so you have to grade them manually, there are a couple of ways to reduce that load. And one of my favorites is that you can grade by question. And I've found that for many activities, like we might ask 20 questions, but throughout the activity, or 30 or 40, but many of them are just kind of formative. They're kind of guiding the student in the way that we want them to go. They're not really testing the student's knowledge or their kind of synthesis of what they've done. And so typically there's just like 2 or 3 questions that really, if you score those, you'll be able to know what the students understood and accomplished in the activity. And so then you can grade by question, and you'll just say, I want to look at these 3 questions, and it will show you everyone's answer for the first one, everyone's answer for the second one, everyone's answer for the third one. And you don't need to read everyone's answer for every question. So that's another kind of way to increase the speed of grading. Another feature that so many of you are familiar with Pivot Interactives, but you may not be familiar with CoLab. So one of the features that we built is that you can assign students to lab groups. We think it makes a kind of more authentic way to do science. It's similar to Google Docs. So like one person could be typing over here and it shows up in the data table of everyone in their group's data tables. And that's a way that they can collaborate better. And like my students, even if I put them in groups, they're like, oh, we forgot to exchange emails. He's got the data, I don't have it, but this way everyone can just have access to the data. And also it reduces grading because then you just have one per every 3 students instead of one per every student. While I'm talking about features, one of the feedback we get frequently is that people love hands-on labs, and we are pro lab, like we love labs too. And we think that Pivot Interactives has a lot of advantages, but like there's some things that you want to just have students touching equipment. And so our data tables integrate with Bluetooth to like Vernier and Pasco sensors. So this is a motion sensor, and if you go to one of our data tables, you can connect them via Bluetooth and then have students make measurements using sensors, and it will stream directly into the platform. And that's nice to have everything kind of collected in one place. So if you've got groups, everyone in the group has it. If there's scaffolding, like sometimes students miss the point, and so we can ask them scaffolded questions to make sure they're kind of on track before they even collect data. And then again, it ties in with the LMS to get the grade pass back. Okay, I'm happy to keep on talking, but I would love to just pause in and check in. What labs do you have problems with? Like, is there anything that comes to mind that you're struggling with as you're going into the school year? You're like, oh, what do I do for this topic? Yeah, Franchette?
First off, I just want to say I love Pivot Interactives. Been using it for a few years now. I do some of my own labs on there, and I do your labs on there, and I do kit labs with my students on there. I mean, we do it all. I love, love, love Pivot Interactives. And nobody paid me to say that. And you just made me fall in love with it even more because there's a couple of things I didn't realize about the collabs. So thank you for that. I didn't realize you were going to be working with Vernier sensors, because that's something we've been buying, those sensors. And now that I know we can use it with you guys, I'm even happier. But I have found one weakness that I would love for you guys to work on.
Okay.
Is when I'm teaching my E&M classes, the circuits, you have like an RL circuit, and I remember that's about it. Like, I'd love to see something with an RLC circuit, just different variations of circuits, even like a Kirchhoff's law, non-simulation kind of thing. You know, somewhere in there. That seems to be where what I would consider the biggest weakness.
Okay, great. Yeah, thanks for that input. Anyone else?
Yeah, this is Jimmy. I would add that something I've talked to Peter specifically about, that this particular group, I think, would be interested in seeing a computer programming element. So you said Colab, and I forgot that y'all do Colab, and I was thinking Google Colab, which is what I do with my astronomy and physics classes, and I was super excited. I use the fact that you can get the data out of Pivot, and I brought it into code that students have written to do data science. But I mean, I'm telling 2 of the founders, having a coding integration feature, either Python, JavaScript, I use P5.js as well as Python or something like it, might be good. And to go with what Franchette, I never got the clearest way to say it, says her name, if there were a way to take microcontroller data into Pivot. So I like to do an RC circuit lab that I'm currently doing in Excel or with code, that you know, the workflow, bringing data from a microcontroller like an Arduino or something like that into a pivot table that they already, a pivot interactives table, not a database, y'all, that they're already familiar with, might be good. And I'm going to say one last thing because I'm able to do it. Matt, you called me about the astronomy lab, and I'm hoping that the HR diagram stuff with data analysis is going to be there because I want to use it in my own class.
It's been on my to-do list for a long time, and with AP adding fluids, it got bumped out by Torcelli. So I've been spending most of my summer on a Torcelli activity, which is the fluid where you've got a tank and then holes in the side of the tank and the pressure increases. So I'm kind of excited about that activity. But yes, hopefully get HR done as well. And yeah, thanks for your support there.
Michael has his hand up too.
Matt, it's a question more than an application. Have you guys considered, or can you expand on the use of uncertainty in the data collection part in the Pivot Interactives? Is there, because for example, when we were in COVID, a lot of the feedback from students when we used simulations is that there was no error. And we know that's not the case in true life. So if you can expand or give us your thoughts on that when we use simulations, something similar to Pivot Interactive.
Yeah, I'd be happy to. Not every activity like draws it out explicitly, but pretty much for every measurement, there's going to be some uncertainty. And actually, some of my favorite activities are those where the simple model, doesn't actually explain the behavior. So I'm going to use that as an introduction to share my screen again and show you some more activities. We actually did a study of this that got published in Physical Review, PER, several years ago, called Model Making and Model Breaking. I can send the link at some point, or maybe Marie, if you can send the link, like just do a Google search for my name and Model Making, Model Breaking, it should pop up, where we had students very deliberately propagate errors and take into account the uncertainty and determine if their results were consistent with a simple model or not. Okay, so this is one of the cases where the behavior falls outside of the range of uncertainty. And so this is a modified Atwood machine. And let me just play the video. So up here, this ribbon was cut, and then Einstein is hanging and pulls the cart, a low friction cart. And then we can move Einstein. So now the total mass of the system remains the same, but now instead of Einstein hanging out here, Einstein is riding. And so now we can do that, and you can see that the acceleration is slow. And so from each of those trials, students can determine Einstein's mass. Like they have enough information to determine Einstein's mass. But they're different. And so, and the reason, it turns out, is friction. But what's cool is that when he's riding, friction makes him seem heavier than he is. And when he's hanging, friction makes him seem lighter than he is. And so even though I think, oh, the reason we didn't get good results is friction, is kind of a boring answer. The fact that in this case, friction can operate either to make him look heavier or lighter, I think is kind of an interesting, cool result. And of course, it's predicated on the idea that it's a real difference. Like you are able to characterize your uncertainty in a way that says, you know, this is a real difference. This isn't just two measurements that agree within our experimental uncertainty. Another one of my favorites is this one. This is our Coulomb's law activity. And so we charge up this electrophorus and rub it on a metallic sphere, and then rub it on a lower metallic sphere. And this is with both of them having a positive charge. And then the upper sphere is lowered, and students can measure the force, reading the balance down here, as a function of the distance. And I'm going to hit escape. Let's see, exit full screen. And I want to show answers and notes. And so as teachers, you can show answers and notes. And so this is the data of force versus 1 over r squared. And so you'd expect it to be a line. You can choose a curve fit. And it's linear-ish. But if you deselect some of these data points on the right, it seems like it improves. And so these data points on the right are when 1 over r squared is large, which means that that's when r is small. So this is when they're getting close together, and we're starting to see a deviation from the kind of ideal predicted behavior. And so students can say, oh, maybe the charge is leaking off. Maybe it's experimental uncertainty. Maybe I just am not measuring more accurately enough. And then eventually, often one student will, with a little prodding maybe, will realize that they're conductors. And so as the spheres get closer and closer, the charges can move on the spheres. And if they're both positively charged, the positive charges are going to flee each other and go to the outsides, the top and the bottom, the top of the top sphere and the bottom of the bottom sphere, so that the effective distance between the charges is greater than you think, and the force is less than you think. So then you can say, what would happen if we did positive negative instead? And if they collect the data, they will find a similar thing happens. It kind of follows the simple model, the straight line, until the spheres get close to each other. And then the force is actually more than you might expect. And again, all of this is predicated on the idea that these are real effects and not just something lost in the noise of measurement uncertainty. I have just one more in this same topic, and that's our ballistic pendulum. And so we fire a marble and have it into a pendulum, and it makes the pendulum swing, kind of the classic activity. This is at a high frame rate, so you can actually see the marble. And it's moving, and then it hits, and you can see that the carbon fiber rod is kind of twisting in interesting ways. And students can make a prediction for how high it should swing. And it turns out that it swings like 6 degrees higher than you'd predict. And so again, students have to determine, is this a real effect or is this just measurement uncertainty? And if it is a real effect, what causes it? Does anyone have any ideas? Jimmy, you're muted. If you were
I was going to say, does the carbon fiber rod act as a torsional pendulum? Like using up some of that energy to make it oscillate?
No.
That was my guess.
Great idea, yeah. Yeah, if you watch it very carefully, there's kind of a clue. So watch the marble right in these frames. And what else do you notice is going on there besides just the marble? Yeah, Stephen? Yeah.
I mean, I'm not sure what the mechanism is for getting the marble there, but I imagine it's some sort of expulsion of gas, and so there's some sort of disturbance there that's adding to the energy or momentum of the pendulum as it moves upward.
Yep. Yeah. So we redid it without the marble. I think that's this one.
Yeah.
And you can see that the pendulum still swings. So the air in the air gun is pretty important. Oh, there was a question about circuits, and you clarified that you weren't interested in simulations, but I do want to say that Pivot has a connection with PhET.io, and so anyone can use PhET, like it's super popular. But in order for students to use regular PhET, they have to build all the circuits. And we have PhET.io, and so we can push this, like we can start the simulation in the configuration that we want. We can randomize variables, we can hide information so they can't see the resistance and they have to determine the resistance, or we can give them some tools like a ammeter but not a voltmeter, and like and it's a really powerful interface. And so it is a simulation, but it really I think PhET.io is great. They take a long time to build, so we're kind of releasing them as they come. But that's something else that I'd like to put on your radar. Okay, it looks like Jimmy had to kick off. And maybe I'll stop there again and just check in. How are people doing?
I just want to say about the simulations. Oh, I enjoy having the simulations on there, but I also like because some of the simulations there's an actual like physical reality lab that, so it's like I like the simulations for like the pre-lab, and then the actual for the real lab.
Marie, how much? I'm happy to show. There's still a few cool ones that I'd love to highlight if we have time, but I don't know when how are we doing time wise? Okay, it looks like we might have. Floyd asks, okay, what does it cost? It's $550 per year per student per year. At the high school level and at the college level, it's $10 per student per semester. So we've really tried to keep it reasonable. Like that's less than a lot of notebooks students buy, certainly less than a calculator. You can't even buy too many mechanical pencils for that. So yeah, we really in order to have a sustainable business model, we have to charge, but we've really tried to keep it accessible to as many people as possible.
So Matt,
Yeah.
So I know, I imagine that a lot of the folks here, because this is PICUP, use some sort of computational modeling software or something like that. And we've been using, I teach in a high school, and we've been trying to develop a series of lessons around computational modeling that uses Pivot. And we're kind of using Pivot in a slightly different way, just that it's a really great digital platform for creating questions and getting, because like if you just use, let's say, VPython or Trinket or something like that, it's difficult to then add in this sort of step-by-step interactive, like, you know, change the code here. How did that, you know, change your simulation? Let's go on and continue to do that as like almost like a learning management system that's attached to the computational modeling software. And so we use a tool called Tychos. It's just it's a 2D Python software that you can just make simulations just like you would in a lot of these different types of platforms. But because it's web-based, and you can probably do this with Trinket, you can probably do it with other things, where you just embed it, right? And so
As an iframe, are you using an iframe?
Yeah.
Okay.
And so it's just there, and we can expand it to full screen, and then the students can minimize it and then see the questions that have to do with that particular part of the activity. And we found that it's because earlier we were just using like a Google Doc or something like that would go along with it, and they were having to switch back and forth, and it was pretty clunky. But the one thing I don't know if this is what Jimmy was talking about, James, sorry. Is there a way to have some sort of API? Because what would be cool is like the students code their simulation right, and then there's something that triggers some sort of communication link between your simulation that you're working on, your coding, and Pivot, so that Pivot could actually know that the simulation is working correctly, right? And based on that can be auto-graded, right? That would be sweet.
Yeah, it's certainly possible. I have to say that our list for like development priorities is a gauntlet. Like for an idea to get made, like it's funny, we prioritize them, and there's like very high, and like if you're medium priority, if you're medium high, like that means you're never going to get built. and so so it's possible. And this is something that I neglected to say. Let me just share my screen quickly again. Probably many of you know this, but there's this chat bubble down here. And so if you want to make suggestions like that, like that's the place to do it. I appreciate hearing it from you directly, but also as you think of things or as you have questions, we really pride ourselves in getting, like we've got great people that staff that. They're teachers and former teachers, and they know their stuff about the platform, in terms of pedagogy, they're on top of things. So as you like, the way that we feel pressure that will increase the importance of features like that is by hearing from you. And that's one way that you can give us feedback. So
I just want to say, Stephen, great idea. Thank you.
and I have to ask, I see there's Richard Schwartz. I knew a Dick Schwartz ages ago. Is that you? In astronomy, I think.
From the University of Minnesota?
Yeah.
I think it is him.
Hi, Matt. No, it probably isn't.
Okay.
We've crossed paths though.
Is it AP?
We've crossed paths through MAAPT.
Okay. Oh, yeah. Okay. Great. Okay. Do we have time for another one, Marie?
We do.
Okay. I promise. Franchette, is it Franchette? Okay.
No H, Francette.
Oh, okay. I think Italian, the CE is a cheese sound, which is what I was doing, which is why it's cello, but maybe it's French, so it's Francette. Okay. I promised you an activity specifically for earth science and environmental science. But like I said, I think everyone, like if you can work this into Pivot, into physics or astronomy, please do it. For this activity, we created a simulated ocean. So this is an aquarium with a simulated ocean. It's got universal pH indicator in it, which at neutral pH is kind of this pleasant green color. And then we have a little birthday candle in there that we're going to light. And you can see that initially the pH is pretty neutral, 7.06. And this carbon dioxide, that's the pH in the water. And the carbon dioxide in the atmosphere is 1.039 parts per million. So about 1,000. Let's see. It's like it's having a little trouble loading. So we light the candle and it starts burning and then it burns out. And while it's burning, let me just see if I can refresh the whole page. You can watch the carbon dioxide in the atmosphere increase, and then a little after that, you can watch the pH in the ocean decrease. Okay, yeah, it looks like it's working. So we light it, and again, we're at about 7 and about 1,000 parts per million CO2 in the atmosphere. So it's burning. You can see, oh, the gasket, the rubber gasket up here melted a little bit, so it kind of came down. And now, wow, the CO2 is already at 25,000. This is time lapse, so it's sped up quite a bit. And then over time, you can see that that's decreasing as the carbon dioxide moves from the atmosphere into the ocean. And you can see the ocean is getting more and more acidic. And the ocean turns this kind of toxic orange color. So that, I think, in that one activity captures so many important things about what we're doing to our atmosphere and our oceans by burning hydrocarbons. So then we redo you can see there's a lot of kind of scaffolded questions to guide students through this, but then we do it again. And this time, this is a piece of real coral that we lower into the ocean. And so it kind of starts out the same. It's a little bit acidic here and a little bit higher CO2 at the beginning. This is burning. The CO2 is going way up in the atmosphere. And then with some time delay, you can see the ocean getting more and more acidic with the pH dropping. But then kind of a curious thing happens. Not quite happening yet. We're still dry. Oh, the pH starts going back up. And so it kind of turned the toxic orange color, but now it's returning back to more pleasant green, and the pH is going back up. And so you all know that the coral calcium carbonate can act as a buffer to the reaction, and so it is kind of buffering the ocean. But then we weigh the coral before and after, and the way that it's able to buffer is by giving up its mass. So it's like the acidic ocean is kind of eating the coral, and that's how it brings it back to stability. So again, just a really interesting kind of big issues in a very small, manageable package.
There was a question about thermal IR cameras that actually might be the question I wanted to ask. There was a peak to I think it was a Stirling engine in one of the
oh yeah,
things that you were showing. I was wondering if you could talk a little bit about that activity.
Yes, let's see. First, I'd like to show this one quickly. So one of the features, we started out with just kind of a protractor, ruler, and stopwatch, but we realized that there were a lot of other things we wanted students to measure. And so we developed the iris tool. And that's, looks like this one doesn't have it. Let's first quickly watch this. So this is in the visible part of the spectrum. There's a rod here with, I think, a copper mass at the end. and then a flame here to heat it up. And you can see it in the visible spectrum, and then you can see the same thing happening in the infrared. So this is the infrared camera. And then this is the iris tool. And if you pause the video, then you can put this sensor wherever you want, and it will read what the temperature is. So it's a way for students to kind of interactively measure temperature, or I was using it for the Hertzsprung-Russell diagram in astronomy, where students are measuring the temperature of stars using kind of how much red and blue and green there is in the spectrum. So that's one kind of interesting IR one. Let me search for Sterling. We have some really interesting greenhouse gases ones also, where students hold up. There are 4 kind of different things that are like transparent in visible and infrared, things that are opaque in visible and infrared, and things that are visible in one but opaque in the other. And those are kind of really interesting. Some things look totally transparent in the visible, but you can't, in the infrared, you can't see them. And some things are like black garbage bags. You can't see through, but in the infrared, you can see details through. So that's another use of the infrared camera for talking about greenhouse gases. Yeah, we got this. And I spent like a day trying to figure out how it worked. I think Stirling engines are so cool. And it didn't work how I thought it did. So this is a thermal insulator here, this big black disc. And it's not a tight fit on the side. So it's not like a piston that's pushing air around. Air can freely flow around it. And so here we put it on, the warm plate heats the lower plate. So we have the bottom is warm, and when it gets going, then it can, the flow of the energy can maintain the Stirling engine going. Yeah, very cool. I don't know if a lot of people do it. I always do heat engines at the end of my class, my intro, when I teach intro physics. I actually haven't gone through this. It looks like they're different. So they're different temperatures. It looks like the temperature is increasing of the bottom hot plate. And then you can see that the speed also increases. Yeah, thanks for asking.
Yeah, I do something like this in my StatMech and thermodynamics course, and we connect it to a pressure sensor that gets plugged into where the, where the oscillating air thing goes, and so we can get pressure curves, which are really nice. I was really curious whether you could see any of the airflow with the IR camera. I think you would need a really high frame rate for that.
We do have one where you can see the airflow, not for the Stirling engine, but for convection. And it's just visually stunning. Let me just see if I can search for it. Yeah, convection is one of those things that it pops up so many places. Whether you're talking about convection in the sun or in the interior of the earth or in the atmosphere. And so what this is it's a frame in a frame. And so the inner frame is the infrared camera and the outer frame is the visible camera. So you can kind of see what's going on. And this is an ice tray that's put on top and then hot water that's poured into the bottom. And you can see it doesn't take too long before it looks pretty much like a fire or the surface of the sun. and you get this kind of beautiful convection currents. And then because we want students to be able to like change parameters and see what happens, we swap it and we put the hot thing on the top and the cold thing on the bottom. And of course, there's like no convection, like they just stop. And being in Minnesota, the land of 10,000 lakes in the summer, like you're just so aware of this, that there's this turnover that happens in the fall when suddenly the top gets cooler than the bottom. And so then you get this turnover, and convection can actually happen in the lake, and fisher people, anglers know about it. But mostly in the summer where the heat is being deposited on the top, like it's super hot at the top, and then you can just feel each layer as you go down because there's no convection. So I think it's fun to kind of tie that to people's personal experience if they've been swimming in a lake.
Wonderful. Well, we're almost to the end of our time, but there is one more question in the chat about, do you have a lab manual based on Pivot Interactives?
So it's supposed to be kind of self-contained. So I would say every activity is the lab manual. And so kind of we guide that, like it's all in there integrated into one thing. If you want to use Pivot as a lab manual, electronic lab manual for other activities, like hands-on activities, you can totally do that. You can just create it. Oh, two more of the features that I wanted to mention that are just super cool. And these are maybe a little advanced, like if you're writing activities, Stephen said he likes to kind of write the activities, is the drag and drop option. So I'm amazed at how it works. Like just the fact of like dragging things into place makes it feel like a very different type of question than a multiple choice. It just feels more kind of intuitive. You're kind of moving things around. So I really I love the drag and drop, and we're doing a lot with that. And then this is like kind of advanced, but I'd be happy if you want to contact me about anything. But if you want to like do this advanced thing, I'd be happy to help you with that also. And that is one of the variable types is collection variables. And so that is basically like a table, and every person gets a different row of the table. And so they can get a different image, and the answers are different, the answer choices, and the correct answer is different. Like you can populate this table so that, and then it's randomized, so every person gets a different row. And that way it can kind of discourage cheating, encourage people to do their own work because you have a different picture than everyone else or different options. And so that's a really powerful tool that I'd be happy to talk more about if you think you want to use those.
Sure. Well, we are coming up on time, but I'll just open it up for maybe a last question or comment if anybody has something.
So I just put something in the chat. So people may remember that we had a computational model for the heat flow program where Kelly built this plate and he could change the temperatures and we could model that. Do we have anything like that for this convection thing that I just saw?
Not in the PICUP exercise sets that I remember. So I'll go with Matt's answer of instead of putting it in the bubble chat, push the big green button on the PICUP site, because we accept requests as well. And I'm sure somebody somewhere can come up with a really great computational model for this experiment. All right. Well, Matt, thank you very much for being here today and showing off Pivot and answering lots of questions. And thank you to everybody else for showing up and for your questions and comments as well. There will be more webinars. We're just kicking off this fall series, so stay tuned. They'll be announced in the events tab on the PICUP site, and you'll probably get email, or if you're in the Slack channel, you'll see it there as well. And thanks again for coming. We'll look forward to
thanks so much for coming. You've been a great group. Good luck with the school year.
Likewise.